Okay, today we are starting the second piece of modern physics. We've already talked about relativity. The next piece of modern physics is quantum mechanics. So we're going to talk about today how light is quantized. Okay, quantum mechanics has its roots back in the late 1800s. At the time, people had Newton's laws, they had Maxwell's equations, and a lot of people kind of felt like, hey, we've got the basics of physics. The fundamental laws of physics are completely understood. Now we just have to understand how to use those laws to do things, all right, to calculate real problems. But at the same time, there were some weird things that people measured that couldn't be explained, and nobody really understood why. And one of those is blackbody radiation. People were studying blackbody radiation, but it didn't quite make sense. All right, as you recall back from the thermodynamics unit, blackbody radiation is electromagnetic waves that are emitted by things because microscopically things are moving, right? Because your body is not at absolute zero, the little subatomic particles that make your body up are wiggling, all right? Electrons and protons, they're wiggling, and accelerating charges radiate, so you're constantly radiating electromagnetic waves, all right? Now, if you were to measure how much light you got per unit wavelength as a function of wavelength, there's a function of frequency, you get the red curve here. So the red curve is showing kind of, I have a kind of an arbitrary y-axis here, but kind of the x-axis is the frequency of light for some object at some temperature. The amount of light it emits at different frequencies is plotted in red, all right? But if you use classical theory and calculate what should be emitted, you get the green curve. So I've got two problems with the green curve. First of all, it does not fit experiment. That is a problem. But there's another thing to worry about, and that's the fact is that the green curve just keeps on going up, higher and higher. It shoots off to infinity. So that implies an infinite amount of energies being constantly radiated through blackbody radiation. So not fitting the experimental curve is a big problem. Infinite radiation is more than a problem, it's a catastrophe. So this phenomena was known as ultraviolet catastrophe, and people were trying to figure out why doesn't our classical calculation match what we actually measure in experiment. Well, a man by the name of Max Planck thought about this, and he was able to come up with a new theory that fit the experimental curve, but to come up with that theory, he had to assume something. All right, so what he did to calculate blackbody radiation, he said, imagine I've got a cavity, right? Imagine I have a metal hollow sphere, for example. There's going to be light and electromagnetic radiation bouncing around inside that cavity because the walls of the cavity are constantly emitting blackbody radiation. Well, Max Planck was able to get the curve that experimentalists measured, but to do that, he had to assume that for any given resonance mode of his cavity, the amount of energy in that was quantized. It had to be an integer, n, times the frequency of the light times a constant, which is now known as Planck's constant. All right? So it's as if the energy in a given mode of this cavity comes in little packets of energy. It's almost as if light is a particle. But wait a minute, in the last unit, interference and diffraction taught us that light is a wave. So it turns out that light can behave both as a particle and as a wave. It's kind of a funky, weird thing, and we'll talk about that in a minute. But for now, the punchline here is Planck's theory works, but it has this weird, funny idea that says light comes in little packets. And the size of those packets depends on the wavelength or the frequency of the light. It's just given by, so the energy of a single packet or photon of light is just Planck's constant times the frequency of the light. Now, why didn't we notice that light was quantized before? Well, it turns out Planck's constant is really small. In SI units, h is equal to 6.626 times 10 to the minus 34 joule seconds. Really tiny, right? So that means that in even low amounts of light, you turn on the dimmest flashlight, and there's just huge numbers of photons per second coming out of that flashlight. So you don't notice that it's coming in little packets because the packet's really small and you've got lots of them, they kind of all blur together. But blackbody radiation gave us a hint that light actually comes in these packets, that light is quantized. Okay, now here's a question for you to think about. What did Einstein win his Nobel Prize for? Going off onto another topic. A lot of you are probably thinking, well, obviously it's relativity, right? Well, it turns out he did not win his Nobel Prize for relativity. He won it for something called the photoelectric effect. So, Einstein wasn't the first person to study the photoelectric effect. He won his Nobel Prize for making sense of the photoelectric effect. It was another one of those things back, in the late 1800s, early 1900s that had people stymied. And here's the photoelectric effect. What people found was if I have some metal surface and I shine light on it, so let's draw light with a wavy line. There's my light coming, all right? It turns out sometimes that light will knock electrons out, and those electrons will come flying out of the surface. All right? And that's, I guess, not too surprising because we knew electrons were in the surface. Light comes in, it gives the electrons energy, it can knock them out. But the way they came out was really, really weird. So they did a bunch of different experiments. And in these experiments, typically what they would do is they'd have another piece of metal up here, and they would put a voltage between these two. So they'd put a battery here. I guess the battery would go the other way, right? And then they'd put a current meter that would measure the current. So they'd hold these two plates at different potentials. The electrons would come out, and they'd get turned around, deflected by the voltage up here. But if the electrons were moving fast enough, they would get past this, they could overcome the voltage barrier, hit this plate, and generate a current. And they would measure the current, and they would see what things affected the current. They would do things like if they would change the intensity of the light, put more power, put more light onto the surface. And what they found is they would knock out more electrons, which makes sense. But there were some other weird things that happened. Now, imagine, how would the current change if you changed the voltage that you applied? You put a bigger voltage, you're going to be able to deflect faster and faster electrons. So you imagine if you had 0 volts between the plates, all the electrons would make it from one plate to the other, or most of them, and you get a big current. As you turn up the voltage, you're going to start deflecting the slower ones, and as you turn it up more, you're going to deflect some of the faster ones, and so forth. So you might expect that as you change the voltage, the current would drop off gradually. But what they found was that the current dropped off very suddenly. And in fact, above a certain voltage, they got no current. Suddenly the current just turned off. There was a threshold voltage beyond which there was no current. All right, so what does that tell us? So there's this sharp threshold voltage, this sharp cutoff voltage. What that tells us is that all the electrons are coming out with about the same velocity. So it's not a matter of I turn up the voltage a little bit and I stop the slower ones. There are no slower ones. They're all coming out with the same velocity. So until I reach the voltage, which is big enough to deflect the electrons at that velocity, I don't see much change in the current. But once I hit that point, I deflect all the electrons, and my current drops essentially to 0. So that's really weird. All the electrons are coming out with the same velocity. That's bizarre. If I were just kind of pumping energy in, you'd expect some electrons to come out faster, some to come out slower. Another weird thing they found, okay, how would the current change if you change the wavelength of the light? All right? Well, as you change the wavelength of the light, you're putting the same power in, but just changing the wavelength. You wouldn't expect the current to change much, right? But it turns out the current does change. But even more interesting is this threshold voltage, the voltage that it takes to turn the electrons around and stop the current. It turns out that that is a function of the wavelength of the light. So the velocity that the electrons come out with, not only is it weird that they all come out with one velocity, it's weird because the velocity they come out with depends on the wavelength of the light. All right, what's going on here? The threshold voltage is a function of wavelength. What is going on? This is really weird. People are trying to figure this out. There's a threshold voltage. It doesn't make sense. The threshold is a function of the light frequency or wavelength. There's no intensity threshold. You'd imagine, right? Imagine waves coming on the ocean and knocking sand out, right? If the waves aren't big enough, you think this wave gives a little bit of energy to the sand, but before it has time to build up much energy, it gives off the energy to the rest of the sand around it, right? So you might imagine, classically thinking, there must be some minimum amount of light power you have to put in before the electrons can gain energy fast enough to get out. But there's no intensity threshold. The weakest amount of light will make some electrons come out. Also, there was no time delay. You'd kind of expect, you turn the light on, it takes time for the electrons to absorb the energy and come out. Turns out they start coming out instantaneously. And the electrons come out very monochromatic, meaning all the same velocity. So, how do you explain all of this? Well, Einstein came along and won a Nobel Prize basically for saying Planck was right. Photons are little packets of energy. Little packets, each photon carries a packet of energy, which is Planck's constant times F. All right, so Einstein's explanation is light isn't this smooth, continuous thing. It comes in packets. And so what happens is light comes in, that packet of energy is given to a single electron. It's not like an electron slowly absorbs light energy from the light wave as a whole. No, what happens is a little packet of energy, a photon comes in, interacts with one electron, gives it all its energy, and knocks that electron out. And that's the basic idea. So, here's how it all works. I have a photon that comes in, and the energy of my photon, let's call it E sub gamma, that's the energy of my photon, is Planck's constant times the frequency. Or, remember, the frequency of a wave is the velocity it travels at divided by the wavelength. So I can also write this as h times c over lambda. All right? I'm going to pause right now and warn you. At some point, we're going to talk about waves associated with particles, like electrons and such. And I may ask you the wavelength, give you the energy and ask you the wavelength of that particle, or give you the wavelength and ask the energy. A lot of students will use this formula, all right? But it doesn't work. This formula is for light, because a light travels at the speed of light. Electrons do not. Okay, but anyway, back on topic here. The energy of my photons in my light coming in, each photon has this energy, hc over lambda, or h times f, all right? Now, I've got this electron. It's inside the surface, all right? The electron is bound. Here's my electron. It's bound to the copper or the aluminum or the zinc or whatever metal it's in, all right? And it turns out it takes energy to get to pull the electron out. There's a certain binding energy that holds the electron in. We know that energy as the work function, and we usually write it as the Greek letter phi, all right? So the work function phi is how much energy it takes to get the electron out. So if the energy of the photon is not bigger than phi, you don't get any electrons, all right? But if this is bigger than the work function, the kinetic energy that your electron has when it comes out, it's the energy the photon gave it minus the energy it needed to get out. And so there's basically one equation that tells us the physics of the photoelectric effect. So if you want to know what the kinetic energy of my photons will be, or my electrons will be when they pop out of the surface, that's just the energy of my photon, or HF, minus the binding energy you had to overcome to get the electron out. All right? And how fast will my electrons be moving? Well, assuming that they're not relativistic, the kinetic energy is just 1/2 mv squared. All right? So v is just going to be, well, that's equal, right, to HF minus the work function. So I can solve this for v, and I'm just going to get 2 over m hf minus psi, right? So I move that over, then I have to take the square root. So there you go. There's the velocity of your electrons as a function of the frequency of your light. You can also replace f with c over lambda and write it in terms of the wavelength of your light. So that's the photoelectric effect. Why is it significant? It's further proof that photons exist, that light comes in little quantized packets of energy. All right, we already talked about the velocity of electrons coming off the metal. Here's an interesting question. Why does ultraviolet light give you a sunburn? What's special about ultraviolet light? Well, Planck's relationship tells us that. The energy of a photon is just h times the frequency, or hc over the wavelength, all right? So the point of the matter is, sunlight is not intense enough to burn you, right? You absorb the sunlight, and you're absorbing energy, but that energy gets dissipated through your body fast enough that you never accumulate, your skin never rises to a high enough temperature to actually burn, you know, in the normal sense of the word burn, all right? So visible light hits your skin, infrared light hits your skin, it heats up a little bit, but then that heat dissipates. But ultraviolet light has shorter wavelengths, higher frequencies, so individual photons have enough energy to tear molecules apart in your body. All right, so an infrared photon, a visible photon hits your skin. It does not have enough energy on its own to tear a molecule apart, so it just heats you up a little bit. But ultraviolet light, these photons individually have enough energy that it just takes one photon to break up a molecule. You don't have to wait for a bunch of them to get together to heat your skin up. It immediately starts causing things to happen, breaking apart molecules in your skin. And that's why ultraviolet light is dangerous. All right. Now, you may be concerned about the fact that light is supposed to be a wave and now we're treating it as a particle. Well, it turns out that light can behave like both a wave and a particle. When it's propagating through space, usually the thing that tells us how it propagates is the wave equation. All right? So it propagates as a wave. But then when I go and measure where the light is, that photon, a photon can spread out and travel as a wave, but when I measure where it is, it has to give me an answer. So it has to show up somewhere. All right? So it behaves as a wave when it's propagating, but then when I measure where it is, it's somewhere. And that's one of the weird things about quantum mechanics is something can be both a wave and a particle. When I ask it to be a wave, it behaves like a wave. If I measure a wave-like thing, it gives me a wave-like thing. If I measure a particle-like thing, where are you, for example, it acts like a particle. So, two-slit interference. We saw interference patterns like these in class, right? But that's really made up of a stream of photons. An individual photon cannot make an interference pattern. When it hits the screen and we detect where it has to show up somewhere. It's just a little blip of light, a really, really tiny blip of light. So how do we get an interference pattern? Well, it turns out these waves, the wave from my photon interferes, and it makes this interference pattern. And the waves, basically, the intensity in that wave tells me about the probability of detecting the photon somewhere. It's probabilistic. All right? So an individual photon, so imagine I have my two-slit interference pattern and I shine a laser at it, but I turn the intensity of my laser down so that only one photon is flying through the air at a time. Each individual photon will make this interference pattern with its wave, but we don't see that interference pattern because when it hits the screen and we detect where it has to show up somewhere, so it'll make a little blip of light somewhere. But the probability where it's going to show up is probabilistic. There's a very low probability it will show up here. There's a bigger probability it'll show up here, for example. All right? So as we build our interference pattern photon by photon, there's more probability of having photons show up in the bright spaces than the dark spaces. And so we get something like this. Photon by photon, we build up a pattern. And after we've acquired many, many photons, we end up with an interference pattern. All right? So the light propagates as a wave, and then it's detected as a particle, as a little blip of light, but where it ends up is probabilistic, and the wave function of the light determines that. All right? So that's how light can be both a wave and a particle. All right, X-ray tubes. Now that we understand that light has little quantized bits of energy, we can figure out how to make really short wavelength light. So the way to make X-rays, is you get a little filament, all right, that gets really hot and boils off some electrons. So I've got a little electron right here. And then what I do is I put a big voltage across two electrodes. So I have two pieces of metal that create a huge electric field that accelerate the electron. And the electron gets going faster and faster and faster. It's going really fast. It's got a lot of kinetic energy. And when it hits this wall, it loses its kinetic energy. It has a collision, and it gives that kinetic energy off as a photon. All right? So if I know the kinetic energy of that electron, it can make multiple photons. It can give some of that kinetic energy to the solid or whatever. But some of these photons are going to come off with energies comparable to the kinetic energy of the electron. So I can make really energetic photons, which means really short wavelength, really high frequency photons, by accelerating electrons really fast and then having them slam into a wall, all right, and slow down really fast. So that's how X-rays are made. All right, remember the energy of a photon is hf or hc over lambda. So if you know the wavelength of light you want to make sure that your electrons have at least that much kinetic energy when they slam into the wall. Okay, another evidence that light is quantized that people found early on was Compton scattering. They found that if you shine X-rays, so now we know how to make X-rays. If I shine X-rays at a solid, so I shine my X-rays in, they will hit electrons. All right, here's an electron. And what will happen is the electron won't absorb all the light. It can't. All right, what ends up happening is I get some light scattered off in some direction, and the electron moves off in some direction. All right? Now, if this were just a wave, you'd imagine the wave comes along, it's going to make the electron move up and down, and it's going to scatter light in all different directions and whatnot. And you get one formula. And that formula that tells you how things happen turns out not to be right. But if you imagine light as a particle, then this is just like a 121 collision problem, right? Where I have some initial momentum, all right? And the initial momentum is the momentum of your photon, all right? And then you've got some initial energy, which is the energy of your photon, and it's just a two-body collision. In the end, you've got some final momentum, which is the momentum of the outgoing photon plus the momentum of the outgoing electron. You've got some final energy, which is the energy of the outgoing photon plus the energy, kinetic energy of your outgoing electron, right? And then you say, well, if the photon scatters off at some angle, conserving energy and momentum tells me how much energy is in the photon, how much kinetic energy is in the electron, what angle the electron will scatter at, and so forth. All right? And just doing it without going through all of the details of the derivation, this is basically by doing a Physics 121 two-particle collision problem. You can come up with this equation here that tells you how much the wavelength of the light coming out is compared to the wavelength coming in as a function of the angle that the light scatters at. All right? So if you use a classical wave theory, you get something entirely different. But if you do the two-body collision, assuming your photon has, the light comes in little packets of energy with an energy of hc over lambda initial, right? Then this is the equation you get, and it turns out this is the equation you measure experimentally. So there is more proof then that light actually comes in little packets. So to review, light comes in quantized packets of energy. We call them photons. And the energy of a photon is just h, Planck's constant, times the frequency of the light, which can also be written as hc over lambda. All right? And then there were three early evidences that light is quantized. It turned out Blackbody radiation, the classical formula for that doesn't work. If you allow light to be quantized in little packets of energy, then you can come up with a theory that fits the experiment for Blackbody radiation. We talked about the photoelectric effect, weird stuff that was happening there that was easily explained just by saying, hey, the kinetic energy of the electrons coming out is just the energy of my photon minus the work function, and the energy of my photon is hf. All right, so allowing photons to exist, allowing light to be quantized in little packets of energy, easily explain the photoelectric effect. Also, Compton scattering. When we measure if I send in some light with some wavelength, some x-rays of some wavelength, and then the light hits an electron and it gets scattered off in some direction theta, we were able to use an equation that told us what the final wavelength would be as a function of the angle it scattered. And that equation came from two-body scattering, treating light as little packets of energy, and that's what gave us the correct theory. So there were three early evidences, early experiments you could do to show that light actually was quantized.